Okay, hello, I'm Junade. I run a team at Cloudflare called the Support Operations team. Basically, we apply kind of operations research solutions to kind of customer problems. I'm going to be telling you a story about something I did with a security researcher called Troy Hunt and something called Pwned Passwords, and how serverless kind of fed into kind of optimizing this service. So why passwords? Why do we need passwords? Fundamentally, it means of authentication, right? So confirming who you say you are. How this is done, it can be done as something you know, something you have, something you are. Passwords represent, something you know from that. And we have two-factor authentication, obviously, so you can use, say, something you have in addition to this. But they're dated. So passwords were first introduced, I think, 1961. It was the timeshare computer at IBM, if I remember rightly, and that was actually breached because the passwords weren't being stored properly, and also users tend to set these passwords quite weakly as well. But the problem really comes down to there's no viable alternative to passwords when we think about it. There's been lots of research done as to looking into specific alternatives, and when they've been compared, no viable alternatives have come out. And the reason why, certainly according to this paper here, is it says they don't account for real-world constraints. So, for instance, when we look at biometrics, when we look at fingerprint, ignoring the aspect of the technology itself being adopted into physical hardware and being, widespread, the other issue is really around there's a proportion of the population who just don't have usable fingerprints. And that brings us briefly on to how passwords are cracked. So dictionary attacks here, I've had to censor out some of the phrases in that dictionary that's there. But some passwords are used more often than others, and using a dictionary of common passwords, you can basically crack them. Computers get faster, users don't. And so one of the things that I think I screenshotted this from some, I think it was a Microsoft password requirements document, and it's basically about where they established kind of complexity rules to try and make passwords more secure. And the eventual outcome of this is actually users tend to actually adopt bad practices after this, and we've learned this over time. This is some research done, I think Microsoft were Canberra. This was basically evaluation of kind of composition rules, and it found that they didn't actually reduce the use of meaningful information in passwords, names, birthdays, etc. And this brings us on to credential stuffing, because often one of the things which comes about with complex password composition rules is people aren't actually disincentivized to stop reusing breached passwords. So when we think about it, people will, if one of their sites gets hacked, they'll use the same password everywhere else. And this is where a credential stuffing attack comes in. You can just go through and you can basically breach a bunch of sites if you have access to one specific set of data. You might be thinking, okay, this is fine, this is in the user's hands. But really it isn't. And the reason why is credential stuffing kind of gets to a point whereby composition rules kind of play into this, and recent NIST guidelines out of the US kind of explicitly make clear that breached passwords should be kind of prevented from users being able to use them. There's other documents and other standards which actually kind of, and I think actually some government departments which are holding companies liable even when they use breached passwords, and it's not, say, the individual kind of company's fault directly, it came from another data breach. They still hold the kind of company responsible there. So in order to improve password security, in order to solve these problems, we can affect three things. We can affect user decisions, so we can try and get them to use password managers to set unique passwords across everywhere, use things like two-factor authentication, developer education, actually getting developers to store passwords in a meaningfully good way, and eliminating the reuse of breached passwords itself kind of ties in with the user decisions components. So encouraging strong, unique passwords, encourage password managers, abolish bad practice composition rules, ensure you don't have an impact, and password expiration policy. I know I've forgotten what they're called, there's some branch of GCHQ in the UK who deal with kind of commercial security. They've been quite vocal about how password expiration policies do quite a lot of harm, and things like how users should be allowed to paste passwords and things like this. So there's some basic things here about developer education. We can obviously talk about security, developer meetups and other such events. We can expose easy hashing APIs, for example the password hash API in PHP, where it makes it very easy to use bcrypt for developers who may not be used to it, and obviously rate limiting and capturing abusive login requests, so someone can't just brute force one account and then use that to credential stuff a bunch of other user accounts, a bunch of other accounts with the same email elsewhere. So that's kind of an introduction to password security, but specifically around the serverless component. I'm going to talk about something I did on a project called Pwned Passwords, and how that fits into the equation of eliminating password reuse across the industry. So we know password composition rules are ineffective. We should instead just outright block users from being able to sign up with breached passwords, and research indicates that if you use appeals to fear, users are less likely to reuse breached passwords if you tell them it's breached. And obviously this is in the latest NIST guidelines that I mentioned earlier. We have massive amounts of data dumps. Password lists are huge, and developers can use API services to check if the password is reused. And up to a few months ago, or actually more than a year ago I think now, what this would involve is either sending the raw password or an unsalted hash of the password, which wasn't the most secure, basically sending the password to an unknown third party unless you want to download an entire database of passwords. And then Troy Hunt, who's a security researcher in Australia, released Pwned Passwords v2. And this contains something which I worked on, which was the k-Anonymity model. So this allows a degree of anonymity whilst you're searching for a breached password. I've got some more information on this on the Cloudflare blog. This has also been covered quite widely. So there's actually a computer file video, if any of you follow that YouTube channel, where they explain how this works. It's been covered really widely in the press and adopted by loads of people from Firefox, 1Password, Okta. Actually, Google recently put out something which uses the similar anonymity model for their way of identifying if a password is breached and notifying users as part of a Chrome extension. And in order to explain the k-Anonymity problem in more kind of concrete terms, the way I'll kind of describe it is, the problem is how so when we store passwords, typically, we try and make those passwords very, very unique. And we will, add a salt in, and we will rehash them with that salt. We'll keep doing that until the resulting password hash is very, very unique. And that way it becomes harder to use things like rainbow tables, where a password is, so in a rainbow table you just have a list of pre-computed hashes. So we solve that problem by making it very, very unique. This goes the other way. It makes the stored password ambiguous. So someone who is searching for it doesn't necessarily know what you're looking for. And it uses a property called k-Anonymity. And that buckets together hashes in a way someone can query a bucket of hashes, but not necessarily know what they're looking for. So actually, hashes can be treated as numbers. They're basically that. They're just hexadecimal numbers. But the other thing is, if you treat them as a string, the other thing you can do is, in order to apply k-Anonymity to them, you can basically keep kind of truncating the hash from 40 characters in the case of SHA-1 down to a certain length as to where you find a minimum size that there is other passwords which exist in the same bucket and other hashes. You can read more about that on my blog post on the Cloudflare blog. If you just Google Cloudflare k-Anonymity, it'll come up. So in real terms, what this means is if you input a password, you SHA-1 hash it, and that's kind of that string over there. 40 characters, you truncate it to the first 5 characters, which is what we computed earlier, and then you do a range search against pwned passwords. And you check if the resulting response contains a hash, and if it does, it's breached. So you don't know whether, when you query for that range, you don't know whether the password exists in that bucket or it doesn't, and it could be any number of several hundred. So this is an example to query just a simple curl request to a range API, and what this breaks down to is you have a bunch of hash suffixes here, which are the remaining 35 characters, and you have a count. So this count is how often that password has been breached. That can be useful for people who want to just block, passwords which have been reused over a certain amount of times. And obviously you can download this data in raw form if you don't want to. That's what GitHub did instead. But this API here is quite widely used nowadays. It's been replicated a few different places, but the main Pwned Passwords API now has a cache hit ratio of, I think it was up to 99% last time I checked, but here it's at 98%. So this is the Cloudflare kind of response from workers. And yeah, so this was where things were a few months ago as well, with them at 94%. I got a bunch of people asking how this works. And the other thing I should add is with ordinary websites, if you're running Cloudflare behind them, you can just go ahead and enable the cache everything page rule. And if it's just a few pages or even a single page site, you actually get pretty high cache hit ratios out of the box. But the problem is with this specific API, because it's taking the first 5 characters of a hash, the passwords which people search for are generally quite distributed. So there's not one particular asset which will give you immediately a very high cache hit ratio. So how do we increase this? So I'm going to show you something. This is actually a screenshot from the developer console in Chrome as to the headers which Chrome sends when you, for example, make an API request to this. So you could make it via JavaScript on the client side, you could make it via a backend API. But when you make a cross-origin request, so an origin to an API on a different host, what browsers will do is they'll send something called an origin header. And this is necessary for cause. It's independent of the referrer header, but it's used as part of the cause process to check if a cross-origin request can be made. And for Cloudflare as a reverse proxy, this translates into a cache key. And the origin header is prefixing everything else which comes out. And that's necessary so we don't break cause. So people who want to treat different origins differently through cause can do so. And then we've got the remaining stuff there, which is the scheme, the host header, and the URI as well. And that is all effectively hashed together. That becomes the cache key. And browsers need to send origin headers for cause, so you can't disable it on the client side. So effectively, through Cloudflare configuration, you're able to remove this from the cache key. And I did this as well with a similar, so this was a project called Unpackage, which was a JavaScript CDN. We sponsored them, typically had lower cache hit ratios, even though they're like, if you go to the React.js site, they're the recommended CDN for React. But in this instance, for example, they wouldn't have had high cache hit ratios. As soon as we enabled this, we found a spike for JavaScript assets, and today it's over 99% as a cache hit ratio. So that was kind of the first trick, just removing the origin. Sorry, go on.
I was just going to ask, so everyone can tweak your cache key, or was that quite a specific thing that certain people have the privilege of customization?
Yeah, so interestingly, this is, for us to be able to make this change earlier on, it would have required a change in at our side. It would have required someone to contact support, it would require them to contact their solutions engineer or something like that and make that change. We're actually able to make it through workers nowadays, so our serverless platform. I'll touch on how that integrates into this equation in a second. But that was kind of the first change we made on this front. But then moving over to workers, so Pwned Passwords did originally have Troy put in place a worker, and what this was for is it allowed it to handle options requests at Cloudflare's edge. So if there's an options request, return the regular cause headers over there. But there was an interesting issue. When I was looking into how to improve the cache hit ratios, I was speaking to someone from a company called EVE Online, a kind of online gaming company. It's a fellow called Stefan. He's blogged quite widely about how they've gone ahead and implemented Pwned Passwords. And actually, when I was looking at example requests he was sending, the casing was different because hexadecimal values are effectively a number. He was representing things like something, for instance, where I would put the hash in all uppercase characters. He would do it in lowercase because that hashing library he was using, when it would return a string, all it was doing was it would render that string using lowercase characters. So I don't expect you to read all of this, but one of the things we implemented kind of in a worker was the ability for it to, so a worker basically sits in the middle when it's receiving traffic. It uses a kind of edge worker syntax in browsers as well. But all this worker here would do, it has a cause behavior as well, would ensure that the hash prefix was made to be in uppercase before that was relayed back through Cloudflare itself. And actually, if you wanted to set an alternative cache key, there is a kind of CF argument there. But obviously the request is transferred, and then the request is actually made later on when the request is leaving Cloudflare's edge. And what this meant is, for instance, we're able to get to a point where the cache key, our customization of the cache key wouldn't have supported us making the prefix or uniform or altering casing on a request, but we're able to do this through a Cloudflare worker alongside other behavior that we want. It's fairly simple to do. And then the final thing, which isn't really related to workers but ties into it, was a lot of the optimization came around how we altered tiered caching. So tiered caching is basically one of the features of Cloudflare Argo, effectively, is how when something goes through Cloudflare's cache, ordinarily it will be served from one data center if you don't have Argo enabled. When you enable it, it will go from Cloudflare location to Cloudflare location over the fastest path of the internet we can find. And one of the side effects of this is as it goes through that path, it will go from, if you're, say, make a request from Manchester, the Manchester data center will label that as a, tier 2 point of presence in Cloudflare's network. We'll label it as something which is, a tier 2, so it will send a request down to a tier 1 before it goes to the origin on the west of the US. And when it does that, there's a place where the cache almost consolidates, and effectively you get higher cache hit ratios. But again, even without this as part of the equation, purely the serverless components of making the cache key more uniform, we're able to dramatically improve cache hit ratios here. So that's everything. That's, if you have any further questions, I'm on Twitter. I'm not sure if you've got any questions here which you want me to answer, or anything else?
Is it best to have like a different sort for each password that you code?
Yes, so ordinarily when you're so salting and peppering when you're storing a password. So if you use an API like password hash, which is integrated into, say, language like PHP, where it handles everything for you, when it does that, it will inject a unique salt into every time you do that hash, and it will keep re-injecting that same salt over and over for however many iterations you want. The difference is there is a practice which isn't really recommended, where it's called peppering, and what you do is you use the same salt across your entire database. It's far better practice to use a unique salt, because that way the password is unique, or the password hash is generated uniquely, so someone can't go through and just generate an entire dictionary list. They have to do that for every single password that's in the database. Awesome. All right. Thank you very much. Oh, sorry, go ahead.
Sorry, just had a quick look at the code. I might have missed something, but it looks like you're normalizing the request to the point where if someone sends a bad request, i.e., let's say they send more than 7 characters, you're actually normalizing to the extent where you never inform someone that they have misused the API. Because the downstream request. So you've got your you're checking the starts with, but you're not doing a like total character length on that the path. So you're always normalizing to 7 characters, and if someone sent more detail, that then could get potentially cached somewhere along the lines. And if they sent the whole hash accidentally, they'd never know that they misused the API, and therefore it will be in some cache buffer upstream of yourselves.
Yeah, so the way the upstream request is made here, so we've got the prefix that's labeled to an uppercase character, but the API itself here is very simple in the fact that the endpoint is always a /range/ on that side. If someone did send the whole string, that would effectively go more downstream, and there are so in terms of how the behavior handles, there's other Cloudflare configurations, which means when a bad request response is done, that doesn't necessarily end up in cache. So that's kind of the way it gets around that. Even though it kind of normalizes it to that where we're getting the prefix.
I think 23.
23, yeah.
So
substring there. Yeah, so if someone sent the whole thing, that would still kind of go through the kind of equation there. But I see what you mean in terms of.
Yeah, so then you go down and fetch at you create new request at 36. Anyway, it's just a.
Yeah, I think it's also the point that Junade was making earlier, which is, what if someone accidentally sends the entire thing? What do we do? Like, how do we distinguish the correct ones from the non-correct ones, right?
Yeah, exactly.
So it's more about protecting actual passwords rather than informing the user of a bad request.
This could give you false negatives though.
Yeah, that's the other. So if someone's done a bad implementation, they don't get the response. I mean, it might be a completely like it's intended.
Again, this is also, mind you, this is for controlling the cache. There is a service that runs upstream that handles error handling and whatnot.
Yes, absolutely. So yeah, the other thing is, I can't remember a while ago when I originally wrote this draft, I think it's been modified since, but I think one of the considerations we did have was preventing people who were putting a full password from that ending up in Cloudflare's cache. So there was consideration made, but I can, if you want to talk about it afterwards, we could go through that, and I can potentially show you the more kind of up-to-date code behind this. This is more just a simplistic demo. I think I omitted some things as well here, just because I didn't want it to run too long and be completely unreadable as well. Now we are.
Thank you. Sorry.
Right, no worries.
What was the impact of the 2-up on allocation?
So, as I remember, originally when we put out Pwned Passwords, I think the cache hit ratio was, if I remember right, it's just over 2/3 because actually, so our CTO at the time, I think it was Troy Hunt, tweeted about this, and I was on the runway at Heathrow. I was about to fly out to the US, and my CTO just messaged me saying, "Oh, this cache hit ratio isn't great," and I said, "Look, I'm on the runway. I'll message you when I'm back up." So initially, one of the first optimizations we did apply was the origin fix. That did provide quite a dramatic change. So I think that was a significant margin, but I think the casing was the thing which pushed it up to the very, very high rates. The tiered caching definitely did kick in, especially as more people started to use it around the world. But I think from the position we went from to where we are, it was about 2/3 cache hit ratio, and then we ended up in a position where it's now, usually in surplus of 99%. In this case, at the time I got these metrics here, it was, what was it? Yeah, 98% over there. But yeah, it does fluctuate between that 1% and 2% mark. Yeah. Excellent. Any more questions? All good.
I have a bunch of them.
Sorry, go on.
Just a more generic question about using password. So I remember. Oh, thanks for the talk. Anyway,
Thank you.
And I remember a couple of years ago, it was something that was coming to the scene, something called passwordless login. I think Netflix was experimenting that, even some other big players. It was basically that you don't have a password on that service, you just have email registered with that service, and every time you need to go through your email to authenticate to the service. I think you have a token that will expire after a while, that kind of stuff. I think it's completely disappeared lately. And
Yeah, I mean, I have noticed it in some apps, but I think it's more the broad question about I guess we've seen the adoption of two-factor auth, but still for that first factor, I don't think there has actually been any viable alternative come out to passwords. And you consider in a lot of cases that there's when we consider about removing passwords and using email, in many cases we're actually moving the problem to another provider which still protects via passwords.
Exactly. Yeah. But I mean, usually, that the problem is that we usually set different password on all kind of service. Sometimes are big companies, sometimes are small companies with maybe small teams, security teams, or maybe with any person in security at all. So it's kind of moving the the security aspect to maybe big players that can invest on the security side.
Yes.
Can I suggest actually? So Slack do the magic link, which is exactly what you're describing. So that is still in use. And there's some really interesting work that's coming right around the corner. It's not established yet, but if you look at Gibson Research Squirrel, it's really quite interesting, and the FIDO Alliance as well. There's some really interesting work that will move away from passwordless. It's just not quite there yet, or the adoption isn't there yet.
Yeah, I think so. I think a lot of the aspect from research so far, when they have been compared with passwordless approaches, there's been quite a few different studies on this. They haven't been able to demonstrate the full factor of benefits across the board for password. Now, there is a question of time and place for them, but so far I just haven't seen the kind of, I guess even at the academic level, there just hasn't been that peer-reviewed material which shows that there's benefits across the board really. But obviously we'll see what comes out of industry on that front, I guess. Sorry, you had a few more questions. Are you going to humiliate me now?
No. It's quite the reverse. I follow Troy Hunt, so I've heard about your work, and I hadn't actually realised you're talking, so I'm a bit enamored. One question about the k-Anonymity model. It seems like it works really well for this use case in terms of you have potentially a very good distribution amongst kind of like the letter samples because of the way the hashing algorithm works. And also you have a really big sample set. I'm just wondering, did you look at the distribution against every kind of, was it 7-letter combination to see what the minimum was as well? Do you have any of those that just out of that kind of random clustering and the reverse there of it, where you might just have a few passwords, and so you could actually go, for this 6-character hash, if anyone was in the middle, they could actually know that it's one of 3, and they could maybe, they could use a rainbow table against those, like the potential, to figure out what those SHA hashes could be.
So in the event of, so this is an interesting problem. It's the question of, correct me if I'm phrasing this wrong, but when you go through the k-Anonymity process, if there's a range you could do with a limited amount of searches, you could, in theory, you could just go through and crack all of them as they're hashed, and then I think there are so you could work out what they are, and then you could work out, in theory, what the user could be sending, right? Is that,
and also that if just through natural distribution, that some of those hashes, some will produce, let's say, thousands. I don't know what the results, and some might produce 6. And the 6 is going to be the problem.
Yes. So this was quite interesting, actually. So we did look through the distribution, and this was actually a very interesting point for me. So actually, this model was rolled out as well to the main Have I Been Pwned API. So when Firefox did their quite tight integration with Have I Been Pwned, the anonymity model also used a similar version, but I think for whatever reason Troy chose to use a slightly more ambiguous version. But with regards to the passwords aspect itself, we definitely did look at the distribution of data, and this was based on Pwned Passwords version 1 data, and more data was added in version 2. But I think on the original blog post I did, there's detailed information as to the different ranges of results we got. I can't, so that there were, actually let me pull it up because it'll be easier to, anonymity. let's see, here we are. Yeah. So this is by the first hexadecimal digit. Smallest prefixes. Yeah. So here we are. Yes, the difference in hashes associated to the largest and the smallest hash prefixes around 1%, and that was the first hexadecimal digit because obviously I didn't want to go to 16 to the power of 5 on a single chart. And this is computations with a new one. So the smallest distribution was 381 in 2 buckets, which are there, and the largest being 584. It was actually quite interesting when you look at the bucket which is the largest. It contains, 5 zeros, because effectively the way a hashing algorithm works is it will left pad if the number's too small. I don't know actually how that works behind the scenes in SHA. I should actually probably look into it. But that was interesting, but nevertheless, it wasn't the case. When you looked at the overall data set, there's one dramatically bigger than the other, but on a new data set, 478 being the smallest, 584 being the largest. So thankfully we didn't come across that particular problem. I know that in applying k-Anonymity to other data sets, there's been kind of similar considerations as to how that can, because k-Anonymity, the guarantee is that there's at least k-1 records, and there's other things like L diversity and those types of attributes which have been used to try and mitigate those problems. But thankfully with hashes, it turned out that they were overall fairly uniform, so that was kind of the chart as it looks. I think I've still got the data somewhere as well. Excellent. Thank you.